Hello students. Now I did a complete video, then I looked to my recording and I saw 000. I was forgotten to start the recording. So now I'm now doing it again. Where shall I begin? Now let f be continuous on some interval and let me take some bounded intervals, so a and b are known, and okay, yeah, you can also let a and b go to infinity or something like that, but that will be so later on how we will go with that. And then you can define your antiderivative, and your antiderivative uh, most of the time then the lower boundary is let free, but okay, let me do this integral here. And then a is known, so a is the lower, in this case, the lower boundary of our interval, and we integrate this, and we integrate the little f. Your t is your integration variable, and then f, yeah, what names you can give, um, as we saw in the chapters before, antiderivative, but often I will call it a primitive function of f. So the the a primitive function of the little f you are trying to integrate. So this is a new name, primitive function. What can we do further on? What can I let you see that we have already done in the lecture here before? If we change the upper boundary a little bit, x plus a little step, and we subtract the the primitive function, we fill in x plus h, and we subtract the function of x, and we divide by x, then we can take the limit from that h going to 0, and if we do, we get the limit from h going to 0, and we have some integral. You have two integrals, you can subtract them from each other, and then you get the, if we assume that the h is positive, you have the lower boundary below and the upper boundary up. You have this one here divided by h, and if we want to approximate this limit, so if you want to calculate, now what can you do? Now you have a little interval, you know your function, so what can you do? You can approximate your integral by a small step times the function fx, and then we have to divide by h, and we have to take the limit from h going to 0, and what do you get out of it? The little f. So the function you want to integrate, you get out of it. And so what do you see in certain sense, if you have that integral from 0 to x, from a to x f t dt, and you want to differentiate it, you were doing in certain sense nothing than filling in the the upper boundary, which depends here on x. You fill in that little f, and you have fx, and in certain sense you were also multiplying by the derivative of x, and the derivative of x is equal to 1. And so you are, in a certain sense, you are calculating here the composition of two functions, so you are using the chain rule. Okay, so you see that if you have that primitive function, or you have your antiderivative, if you calculate the derivative of it, you get your small f out of it. Now, what further on? If we are integrating from a to b f t dt, and you know a primitive function, and maybe I can better fill in here t, then you can fill in the upper boundary in the primitive function, and then you subtract the value of the lower boundary. So if you have a primitive function, and if your derivative is equal to f of t, now then you can fill in those boundaries, and you get the value of the upper boundary minus the value of the lower boundary. And oh yeah, and this is only going well, but that I have already said to you, only if f is continuous. So be careful with that. Yes, what to do further on? Now I want to make some. I want to say something to you, and that is that the integral from 1 to x 1 over t dt, that is just known as the natural logarithmic of x. And in certain sense, uh, yeah, people did not like to write down this integral every time, and they give some name to it, and that name, that is the natural logarithmic of x, and therefore they always will tell to you, now the logarithmic of 1 is 0. Now see what happens if you fill in the upper boundary 1. You get an integral from 1 to 1, and you know an integral from, if the upper and the lower boundaries are equal, that you get 0 out of it, and therefore your logarithmic of 1 is 0. And you see here also, if you take the derivative of this integral, now what to do, then you have to fill in that x value in the function you were integrating, and that gives you 1 over x. Here you see the natural logarithmic of x, but in certain sense the ln is nothing else than a name for some integral. Now let's see some more examples of primitive functions, and how to use them. For instance, if somebody gives you that the derivative of a capital F is equal to x, now then you can calculate your primitive function, and what do you know? Here you see x to the power 1, and if you will integrate it, I think that you will get x squared, but if you now differentiate, you get 2 times x to the power 1, and that 2 I don't see. So if you put some 1 over 2 before, then you see that the derivative of that expression there gives you the value of x. That is going well. And now a primitive function, there is not just one, but there are a lot of them, because you have always that constant c. And don't forget, it is important. So if there is asked you to calculate primitive functions, you know there will always be some constant c, unknown constant c. Put it always behind it, please. Yeah, and what can you now do? For instance, if you have the integral of 1 to x t dt. Now what can you do? You know now that the primitive function will be 1 over 2 times t squared plus some constant, and you have plus some constant, and you have that lower and the upper boundary. But here you see that the lower boundary is known, the upper boundary is in a certain sense known, and if you fill in, you see that the c falls away, and we get out of it minus 1 over 2x squared minus 1 over 2. And you see also that if the x is equal to 1, you get 0 out of it. And therefore, if we calculate those integrals and the lower and the upper boundary are known, then often that c is kept away because we know that that c will fall away by filling in the lower and of the upper boundary and the lower boundary. Okay. Then we have then we can have that somebody gives you some integral of some small f, and that the upper and the lower boundary depend on your variable x, and you want to differentiate it. Now, what can you now do? Maybe you can first find your primitive function, but that will not be easy always, and maybe it does not exist. That can also be the case. So, but let me assume that that unknown function is known. Now, what then? Then you know that integral becomes equal to the primitive function of the upper boundary minus that primitive function of the lower boundary, and then you have to differentiate this one here. And here you have to choose the chain rule. And if you use the chain rule, what do you get out of it? The derivative of the capital F is the little f, so you have the little f working on g times the derivative of g minus the little f working on h of x times the derivative of h. And I hope that you see that in certain sense you don't need your primitive function, because you see here out of that expression here that you have just filled in the upper and the lower boundary in your little f, and then you have multiplied it by its derivative. You have just used the chain rule, and in certain sense you don't need your capital F, you don't need your function you have here. It goes here all right. Now then you have to know certain integrals just that you have in mind. Now I have already given this one here, integral of t dt you get, and then you have 1 over 2 times x squared plus some constant. Don't forget the c. You can also integrate 1 over t dt, and you know there is given some name to it, that is the ln of x plus some constant. Don't forget those constants. And now you can go on with it. For instance, the integral of an unknown lower boundary to x, 1 divided by 1 plus t dt. Now, think to yourself, what can come, what function I can differentiate to get 1 divided by 1 over t. Now, I think that the ln of 1 plus x will be a very good one, but also plus some c. And so here you see the ln of 1 plus x. If you differentiate this to x, now you get 1 divided by 1 plus x, and here you see fill in the upper boundary in that expression there. You get 1 plus 1 over x and times the derivative of x, and that is 1. Yeah, that is going well. And so you have a lot of integrals you know already. And for instance, the derivative of the primitive function of the sine will become minus the cosine of x plus some constant. Be careful, because if you differentiate the cosine, you get minus sine of x, and with the minus sign you have there staying, you have the sine of x, but be careful. And also the integral of the cosine of t, that is easier, that is just the sine of x plus some constant. No problems with the all kind of things. Then we have already calculated the derivative of the arctangent. Now, and we know that the derivative of the arctangent is equal to 1 divided by 1 plus x squared. So if you have some integral like this one here, 1 divided by 1 plus t squared from some unknown lower boundary to x. Now what do you get out of it? Here you get out of it the arctangent plus some constant. Differentiate the right hand side and you get the function you have here inside your integral. And yeah, you are filling in the 1 over, you're filling in x, and so you get 1 divided by 1 plus x squared. Now, and go so on, and all those integrals you have to know in mind, out of mind, but you can also, um, at the exam, there will also be given some table of certain functions so that you can which can are used maybe during the exam. Other one important one is the 1 divided by cosine squared. Now a primitive function of it is equal to the tangent of x plus some constant. Now, and I think that we have now done most of the things we have now done, and with all those you can do a lot. So let me try certain integrals. For instance, if there is asked to you to calculate a primitive function of this one here, t plus 5 divided by t to the power 3 divided by 2. Now, directly finding one expression that I cannot do, but you can here cut that problem into pieces. You have that piece t divided by t to the power 3 over 2, and you have the piece, the integral from unknown boundary to x, and then 5 divided by t to the power 3 divided by 2, and then you can do for those separate parts, you can try to calculate your primitive function. For instance, if you have here, if you write it out, you have t to the power, what do you have, minus 1 over 2. And so if you integrate it, what will we get? We will get t to the power, now you have to add 1, so you have the integral of t to the power plus 1 over 2, and if you differentiate this one, you get 1 over 2 times. I don't see some constant before, so I think it will be good to put there a 2. Then if you differentiate 1 over 2 times 2 gives you 1, and that is exactly the value which is staying also in that integral. There is staying there 1 times t to the power minus 1 over 2. Now, and that between the uh, between the unknown lower boundary and x. Now, and the other one, what will we do? Here we have what is staying here. Here is staying t to the power minus 3 over 2. And so if we want to make a nice expression of it, what will be, now we have then t to the power, and you have to add, so you have 5 divided by 2. Now if you differentiate it, you see already 5 divided by 2 times something. Of 5 you have already, but the dividing by 2 I don't like, so I put times 2, and also between that unknown lower boundary and that upper boundary. Now, and if you now write it out, you get 2 times the square root of x. Yes, sorry, and then I have forgot, I have made some error. I have to add 1, so I have not 5 over 2, but I get minus 1 over 2. So that was some error I made. Be careful. So this is the good one. And if I now uh, make some calculation, I don't see the 5, so I have also to let's stay the 5 because I can nothing do with it. So I have 5 times 2 times this one. And if I now differentiate this expression here, if you take off this expression, if you differentiate it to your t, you get this out of it. So that is going well. And what do we get out of it? And then I see some other problem, and I see that I have also to not to forget, and that oh terrible, you see how much problem, how much errors you can make. I have forgotten to to keep the minus sign, because be careful, you have the minus 1 over 2. So if you differentiate, you have minus 1 over 2 times that one expression here. So we have here out of the solution minus 10 divided by the square root of x, and then we have some unknown boundaries, so in an indefinite interval, so we have to also to put that constant there. And now everything goes well, but be careful. Yes, the derivative to t variable of minus t times t to the power minus 1 over 2. Now if you differentiate it, you have minus t times minus 1 over 2 times t to the power, and then you have to subtract 1, and so you have minus 3 over 2. And you see, if you multiply those together and you divide the 10 by 2, you get out of it 5 times 10 to the power minus 3 over 2. And so you see that how you can look if your calculations are right or not. Now, then maybe we can also use some of those rules we have already done if that in that other chapter, in the chapter before. Now for this integral, sorry, dy. Now the y is the integration variable. The integration variable you can give all names you want. Now in this case you have y. Now what do you see? This function is even, and so we know that you get out of it 2 times the integral from 0 to 2, and then the absolute value of x that falls away, your because between 0 and 2 your y is positive, and you have y squared dy. And what do we see? We see if we differentiate y squared of the exponential function of y squared, if we differentiate this one, what do we get out of it? Now, using the chain rule, you get also that exponential power keeps staying, but you have to multiply by the derivative of y squared, and that gives you 2y. Now, and you see here that you have also 2y. So what comes out of it? The primitive function becomes equal to exponential power of y squared between the boundaries 0 and 2, and we get out of it e to the power 4 minus 1. Now that gives you some value. And so you can go on and on by still using the primitive functions I have just asked to you, or those rules. And I have already given in chapter 5.4 this one here. Now, what to do? In a certain sense, we don't. Yeah, we can also cut it into pieces because I don't see any what you can do otherwise. So you have y divided by 1 plus y squared, and we have that integral from -1 to 1, and then 4 divided by 1 plus y squared dy. Now, what do I see? Um, this function is an odd function, and if you have an odd function and your integration variable is symmetric around 0, then you know that there comes 0 out of it. So without doing too much, the first integral becomes 0, no problems. And then the other one, I see here the 4 you can put before the integral, and then you get 1 divided by 1 plus 1 squared. That is, it gives me the derivative of the arctangent of y. So you have here 4 times the arctangent of y between -1 and 1. And so we get out of it 4 times the arctangent of 1 minus 4 times the arctangent of -1. Now, and what do we get out of it? The arctangent of 1, we know that is pi divided by 4. And the arctangent of -1 is minus pi divided by 4. And so you see that you get pi plus pi, and that gives you 2 pi out of it, this integral. Now, and so you can go on and on with a lot of those integrals using all those rules which are already given, the primitive function I have already given. Now, if you have, if this becomes your problem, so you have an integral. In the lower boundary, you have the cosine of x, and then you have to integrate this one here, t divided by 1 plus t at the exponential power of t, and you have to differentiate this function here. Yeah, what can you do? You can first try to calculate that integral and then differentiate, but why should you do? You know that out of this integral you can fill in the upper and the lower boundary and then multiply by the derivatives of that upper and lower boundary and subtract those values of each other. Now, if you fill in one, okay, but the derivative of one is a constant, so you get here some expression times 0, so there you don't see anything of it. So in certain sense you have 1 plus the exponential of 1 times the derivative of 2x of 1, and that becomes 0. And then the lower boundary that you have always to subtract, and so you have fill in the lower boundary, you get the cosine, I fill in that function, so you have the cosine of x divided by 1 plus the exponential power of the cosine of x, and then times the derivative of the cosine, and just use that rule of differentiating those integrals and fill in the upper and the lower boundary, and don't forget to multiply by its derivatives. You are just doing a kind of chain rule. And so what do we get here out of it? We get out of it 0, and the derivative of the cosine is equal to the minus sign, so you have plus cosine x times the sine of x divided by 1 plus the exponential power of the cosine. And here you have your derivative. And be careful if the derivative of the cosine is the minus sine of x. No. And so you can go on with a lot of those integrals. What I want to say more about it? Yeah, because I just have one. I have now just 1/2 hour. Uh, Maybe I can do 2 more examples or 3 or more examples, and then also tell you about something about that integral. Let I do the next video.